Welcome everyone. I'm Joop Schaye. I'm from Leiden University and I'm the chair of the SOC. And I'm very happy to chair this final plenary session. It's been a very exciting week and we have a couple more very exciting talks ahead of us, as well as a closing ceremony. We'll start with one of the traditions of the EAS, which is an update from the European Southern Observatory. This year, the ESO report will be a talk given by two people. The first will be Ciska Kemper. Ciska Kemper started actually her career in Leiden as a master's student. Then she went to Amsterdam where she got her PhD in 2002. After that, she moved to UCLA as a Spitzer Fellow and then spent some time at the faculty of the University of Virginia, Manchester, and also in Taiwan. And since 2018, she's the program scientist at ESO. And her main interest is the life cycle of dust and the interstellar medium. The talk will be given together with Michele Cirasuolo. Michele obtained his PhD in 2004 from Ciska. After that, he became a postdoctoral fellow in Edinburgh, and he stayed there for a decade, I think, in the end as senior project scientist, and he's still an honorary fellow there. Since 2015, he's the ESO program scientist for the ELT. His main interest is high redshift galaxies and instrumentation. He's also the instrument scientist for KMOS and the PI for the Moon's multi-object spectrograph for the VLT. Michele, you can start sharing your screen.
Good morning, everyone. In this presentation, we will give you, as Joop said, the traditional report on the activities and achievements of ESO since last meeting. This talk is shared with Ciska, program scientist from ALMA, but also we got a lot of input from Bruno Leibengut and Antoine Meran, who are the program scientists for the VLT and the VLTI respectively. Just one slide, mostly for the young generation. They probably don't know much about ESO. So ESO is an international organization which is supported by 16 member states across Europe. And we also have a strategic partnership with Australia. And the main aim of ESO is to develop and operate state-of-the-art facilities for astronomical science. ESO runs several programs. You can see them here. So La Silla Paranal, which include La Silla, Paranal with VLT and VLTI, but also APEX, the millimeter telescope on Chaknantor. The ALMA program, which is done in collaboration with NSF and Japan. And then there is the program for the construction of the extremely large telescope, which is ongoing. And then under development, there is also the program for partnership and operation of the southern array of the Cherenkov telescope, which will be operated by ESO at Paranal. Before giving you some updates on each of these programs, we thought it would be nice to provide you some highlights of the science that the ESO facilities have been allowing over the last year. This list is absolutely not comprehensive or includes all the things. It's just a very quick snapshot of the science across the various facilities and also across the various science domains. So this is one example from a recent paper from Nieleman. What they used ALMA to observe in C2, a galaxy, a redshift 4.2. And what they found is that the galaxy shows a very well-ordered rotation curve with rotation up to 270 kilometers per second. Now, this galaxy, it's at redshift 4.2, which means is only 1.5 billion years after the Big Bang. So very short time scale to form a very massive cold disk, which already shows a very ordered rotation curves. Therefore, this is very important to understand and put this in the context of galaxy formation at high redshift. And therefore, what is the mode, for example, the cold mode of galaxy accretion to provide in a short time scale already enough cold gas inside the galaxy to have such a massive cold disk. Not just new data, but also the archive is a very powerful tool to do science. And this is an example from ALMA, but there are plenty of others from VLT, VLTI, VISTA, and the other ESO facilities. This is just an examples from the A3 Cosmos project, which they just purely mining the ARMA archive, they managed to combine all the available observations in the cosmos field and obtaining a very deep contiguous, effectively a very deep contiguous survey. So the power of the archive is very strong. Another very successful story of last year is the measurement of the spatial precession around Sagittarius A star, so the supermassive black hole at the center of our galaxy. This is a long stretch of observation that culminated after almost 30 years of observations of the S2 star using the ESO facilities, NACO, Symphony, and in particularly the new instrument Gravity for the VLTI that used the combined 4 UTs to make very accurate observations. And as you can see from the top panels here, the data are very well fitted by the general relativity prediction for the spatial precession compared to what you would have seen if you were just in pure Newtonian gravity, which is this dashed line. So this data confirm that there is a spatial precession around the supermassive black hole, and that is depicted in this video you can see here at the bottom, where S2 goes around the central black hole, which is this point here at the bottom of the graph. The quality of the data is also extremely good to allow other measurements. So for example, to check if there are other objects close or nearby to the central supermassive black hole. This is a plot where you can see at the bottom the potential mass of the intermediate mass black hole, if there was one, and versus the semi-major axis. And all these shaded areas are zone of exclusion. So previous studies have already excluded part of this parameter space. And then you can see the recent gravity data managed to exclude almost all the remaining free parameter space. And this is telling us that practically there are no many possibilities for intermediate mass black hole around the supermassive central black hole. So in some sense, Sagittarius A star is a very lonely wolf in that part of the universe. And I pass it to Ciska to continue on some science highlights.
Okay, thank you, Michele. So the next science highlight that we want to present to you is this work that was done on a luminous blue variable in a dwarf galaxy, which is at a distance that you cannot look at the stars individually. So you have these unresolved observations. And these observers wanted to observe this object and were astonished to discover that the typical wings that you would see on the H alpha and H beta line profiles actually had disappeared. So I don't have the pointer, but you can see it in the light blue line in the top of these two plots. You see that there is no more wing to this line. Which means that the dominant LBV in this galaxy has somehow stopped producing its stellar wind. So somehow something has happened, and this has happened over a period of about 10 years, because 10 years ago we could still see these wings, and some tantalizing possibilities present themselves. One of them being that the star somehow dropped in luminosity and increased temperature, along with the production of some dust obscuring the star from view. But another possibility is that this object went into directly collapsed into a black hole without producing a observable supernova. Next slide, please. Another result going more close to home is about the shape of asteroids as observed with SPHERE, where observations of the asteroid 10 Hygieia has shown that it's actually nearly spherical and doesn't really show any significant cratering on its surface. So you can see that here in the left panel of this figure. And this is now the smallest known object with these characteristics. And this object is known to have formed from debris that reaggregated under self-gravity after a collision. And because it's so spherical and doesn't show any surface features that that indicate cratering. These are basically the signature of a minor planet, and this object now holds the record of being the smallest minor planet that we know. So also a very exciting result. Next slide, please. Now going to planets around other objects. Gravity on the VLTI has done some interesting, made some interesting progress here. So the top result here is work on HR 8799, which has a number of planets, and one of these planets has observations in the past with adaptive optics. As you can see on the right in the panel labeled AO, you see all these gray marks, which are the AO measurements. The gravity measurements, which has much higher precision, actually helps to confine the possible orbits of this object, of this companion E to HR 8799. And it actually shows that this object is probably not coplanar with the other exoplanets in the same system. And then another result from gravity with on exoplanets is near-infrared spectroscopy of the CO band heads in companion C to Beta Pictoris, showing that its composition is very similar to the actual star itself, indicating that it formed by a core accretion formation scenario. Next slide, please. Some synergy between ALMA and VLT is also very welcome, of course. We really are looking to get more of that. A very exciting result is this work on PDS 70, a T-Tauri star, which actually has companions. The first companion was discovered with sphere in 2018. And then in 2019, it became clear that there were actually two companions, and both of them could be seen with MUSE as being visible with H alpha emission, which indicated accretion onto these two companions, these two exoplanets. And ALMA continuum emission then allowed for estimating the mass around these or involved in the formation of these exoplanets. And at first an upper limit was placed on the material, circumplanetary material around companion B of 0.01 Earth mass. Then the analysis of the second companion showed that it was about 2 to 4 times 10 to the minus 3 solar Earth masses in the form of dust. And then if you take into account the typical dust to gas ratio, this is actually enough to form a moon, an exomoon, to accompany this exoplanet. Next slide, please. Now we have to get back to the reality of every day. I mean, all these science results are very exciting, but unfortunately our reality is that we're dealing with the COVID-19 pandemic, and ESO has had to respond to that. And what has happened in the past few months? Well, first of all, we were forced to close the observatories. La Silla and Paranal went into a safe state as of the beginning of March. Construction at Amazonas of the ELT continued until about a week ago, but is currently also in the safe state. Similarly, the ALMA observatory, all the sites of it, the OSF, the actual high site, and also the offices in Santiago are currently in caretaker mode, which means that they're visited on a daily basis to make sure everything's okay. At the headquarters in Garching, we are now seeing a limited return of personnel to the office on the safe conditions after having been closed basically for 2 months. And we are ramping up over time. But in Santiago, unfortunately, the pandemic in Chile is not fully under control yet. We are limited to having just essential services on site, and everyone is still working from home. However, plans for reopening have been developed. They've been developed relatively early on, a very clear definition of phases of reopening, and we're moving from phase to phase as conditions allow. And this means also that we at some point will start operating again in a restricted form, initially just with selected science operations, but gradually building up as conditions allow. Like I said, the situation in Chile is not allowing the reopening yet, but we are reviewing the situation regularly, very regularly, to recommend changes to this situation. Next slide, please. For the organization itself, the effect has been that all the operations have stopped, as I said before, and all travel and in-person meetings, both on and off-site, have been suspended. But obviously, we're not twiddling our thumbs. Stuff is still happening, and what we're doing is, for instance, software developing and maintenance. This is a really good time to keep going on that. Data processing and archive maintenance. So in case of ALMA, for instance, the backlog has been completely minimalized now. Technical development is definitely possible, both on-site in Garching and in the member states, the institutes that we're working with. Some labs, most labs have been closed, but are now reopening. So actual work with physical components can happen. But what has never stopped is work that didn't require a lab and could be carried at home, such as design of components and also working on documentation. This has turned out to be a great time to work on documentation. This is also true for the programmatic aspects. Also, again, a lot of work on documentation has been happening. And of course, we are positive, looking forward to the future, and we're preparing for future observing cycles. Another opportunity that many of us took is to engage in staff training and improve our skill set. And science meetings picked up also for the staff initially, internal meetings via Microsoft Teams and all that. But actually, gradually, we've also moved this into a more external mode by inviting outsiders to colloquia and other talks, and now even organizing virtual conferences. So that's happening as well. Next slide, please. And then we get to the news about the individual facilities. So first, let's talk about ALMA a little bit. And I will focus on the development, when I talk about ALMA development, I'll focus on the development that's happening in the EU region. Because operations are closed anyway, so there is not really any point about talking about the effects for observers. So just talk about the development on sich. So our main project right now is the production of Band 2, a Band 2 receiver, which is going to operate from 67 to 116 gigahertz. At least that's our plan. We have obtained approval from both the ALMA board and ESO, STC and Council for pre-production. And all the corresponding contracts have been signed. So it's going to operate from 67 to 116 gigahertz. This is the entire atmospheric window that it shares with Band 3. So it overlaps in frequency range with Band 3. This means that Band 2 is going beyond the original specifications, the design specifications. The approval has been, or the contract is for 6 pre-production units, and it will be followed by a gate review at which a decision will be made for the full production. The contract is signed by a consortium consisting of NOVA in the Netherlands, Chalmers in Sweden, and INAF in Italy. And they are in charge of putting together these 6 pre-production units. And this is done in collaboration with us at ESO and with contributions from NAOJ in Japan, NREO in the US, and the University of Chile. Next slide, please. Other news on the development front is that in Europe, we also are in charge of producing or upgrading the existing ALMA observing tool. And approval for that has been obtained recently as well. And this project is led by the UK ATC in Edinburgh. And the project, the development project, so now it's acquired the status of a development project, has officially kicked off just earlier this week. So that is very exciting news as well. The idea is that this observing tool will be in place for cycle 10 in 2023. Then another development project is Ariel, led by INAF in Italy, which is reprocessing cycle 2 to 4 data with the present day imaging pipeline. And it has delivered its first set of images to the archive, and these have been successfully ingested into the archive. And the plot here on the right-hand side shows the in the green line, actually, how much the processing is ahead of schedule, which is indicated by the thin gray line. So that's great news. And then finally, before something becomes a project, we have development studies. And so to investigate concepts for development. And we have selected 5 new development studies from the 2019 call, which was put out last year. And contract negotiations are on the way with the PIs and the teams. And so far, 1 project has kicked off. And this is a project with the Laboratoire d'Astrophysique in Bordeaux to study the improving the digitization efficiency on ALMA. Next slide, please. And then finally, the final slide on ALMA news is news about what it all means for you as an observer. Well, as I said before, ALMA has been closed due to the pandemic since the middle of March, halfway through cycle 7. We did issue a cycle 8 call for proposals on 17 March. This was almost immediately postponed on the 19th of March and then later suspended and ultimately withdrawn. This means that we are not going to have any new cycle 8 projects, but we still have half a cycle of cycle 7 projects. And we have decided that they will remain active and in the queue until 30 September 2021. And as of March 2021, we will basically repeat the configuration schedule as was planned for the corresponding month in 2020. So that will give us a chance to execute those projects, provided the telescope is open by then, obviously. Cycle 8 now starts in October 2021. And a new cycle 8 call for proposals will be issued in March 2021 with a deadline in April 2021. What will be new? Well, there will be several things new, but perhaps very noteworthy for the proposal submission and review process is that we will now have distributed peer review, which means that if you as a PI submit a proposal, you will basically get about 10 proposals back to review, and you have to rank them, and then we will collate all the rankings from all the PIs and make a final ranking. So we basically circumvent the whole panel review system. It's just a different approach. We will also do dual anonymous review, where it's no longer possible to see the identity of the proposers. Panel review will remain in place for larger time requests, certainly for large proposals, but also some of the larger regular size proposals, we have yet to decide on the threshold time request for that.
3 minutes.
Yeah, thank you. Michele, it's your turn.
3 minutes, so okay, I have to run then. Regarding the Paranal, La Silla Paranal, you can see there is a very healthy situation in terms of instrumentation development. You can see here, CRIRES, which is a high-resolution spectroscope, has been mounted on UT3, and it's now just waiting for the telescope, the observatory to reopen to start commissioning. The use of gravity as a fringe tracker for Matisse has been commissioned and offered. ERIS, which is an AO-assisted imager and spectrograph for the VLT, is in the final assembly phase, and we expect to have it delivered, so with the final acceptance in Europe, preliminary acceptance in Europe by the end of this year, beginning of next. MOONS is a multi-object spectrograph, which is in integration phase. Foremost is another multi-object spectrograph in integration phase as well. And because Foremost is also offered to the community for public service, we request a letter of intent. We received 30 of them, and from 19 of them, we invited proper proposals to be submitted. Also, in terms of upgrades and future project, the FORCE upgrade has completed the phase A. MAVIS, which is a MCAO, multi-conjugate adaptive optics in the optical feeding imager and a spectrograph, almost completed the phase A, just few pending action. And CUBES, who is a high-resolution spectrograph in the UV, starting the phase A. And also on La Silla, NIRPS, which is the near-infrared high-resolution for 3.6, and SOX, which is the Sonovex shooter on the entity, are in their integration phase. Also looking forward, what's going to be the future of the VLT and the LTI in 2030 is a very important thing for ESO. So to look at this, we had a workshop in June last year, which was very well attended with lots of people with instrumentation background. But we also tested what is the expectations and the driver science from the community with a poll that I hope many of you contributed, and all this has been injected into the exercise. Out of this, we had 3 white papers from 3 independent teams, which has been reviewed by the STC at the last April meeting. And from these, there were clear priorities for 2 possible instruments. One is called Gravity Plus, which is an upgrade of Gravity. Another one is Blue Muse, which is Muse but extending in the blue side towards the UV. And the planning phase for the phase A of these 2 new instruments is starting now. We're also looking at how the community can have a better use and optimize the science output of the ESO data across the entire data flow from the phase 1 up to the science exploitation. And for this, there's going to be an online workshop, 7th and 8th of September. And you can see, this is the link. You can go to the ESO website and hopefully many of you will register. The idea is to really go through all the phases and help on how to write a better proposals, how you can optimize your observation phase 2, how you better can read the data, but also collect ideas on how to implement the old system. And finally, regarding the Extremely Large Telescope, last year has been extremely successful in progressing with the construction. Started in 2014, and it comes with a comprehensive suite of instruments. The work, as you will see, is very well underway, and we are forecasting first light towards the end of 2025. You can see here a picture of the main structure of the telescope, and I'll take you through some of the recent achievements. So the primary mirror, which is 39 meters in diameter, is segmented in 798 individual mirrors. They're all now in full production. You can see here the casting process done a shot. They are then shipped to Safran-Reosque in France for the final polishing. Then they are integrated with the support structure from VDLPI, where we also insert the edge sensors and the positioning actuators that allows the mirror to be placed in the exact position on across the primary mirror. The M2 and M3, which are the other 2 big mirrors in the ELT, which are of the size of 4 meters each. Take the Vista mirror and it becomes a secondary or tertiary mirror for the ELT. Both M2 and M3 has been cast from shot, and now they are in polishing at Safran-Reosque. You can see here also the cell that will host and support these 2 mirrors inside the structure. ELT is a fully adaptive telescope in the sense of the adaptive optics is done inside the telescope, and it is done to correct for all the vibration and turbulence of the atmosphere. And the main actor in this is what we call M4, which is a mirror where the actual mirror is a very thin shell of 1.9 millimeter thick. 6 of them are already completed, and they are supported by this silicon carbide, very sturdy body. And behind here, you can see these holes where we have more than 5,000 actuators that are capable of moving and changing the shape of the mirror up to 1,000 times per second to provide all the adaptive optics correction that we need. And here you have the M5, which is the final tip tilt mirror, again at 1 kilohertz. Regarding the dome main structure, also here has been a lot of progress. You can see here components of the actual main structure being built by the contractor, and also the site on Armazones. Until a week ago, there was work ongoing here. And you can see the central excavation for the pier, and then the outer part where we have the auxiliary buildings. These all the foundations with the concrete, and just again, to give you a scale of the scale of the people compared to the outer edge of this wall. It's 100 meters in diameter. It's going to be 80 meter tall. Also on the instrumentation side, a very good progress. So Mikado is the first light imager, which passed PDR in 2018 and now is going to have FDR, which is the final design review in 2021, is fed by an adaptive optic module called Maori, which is going to have the preliminary design review in 2021. Harmony is the other first light instrument, which is an IFU monolithic, again, passed PDR in December 17, and is going to have FDR next year. And METIS, which is the imager and spectrograph in the mid-infrared, just passed the preliminary design review in May last year, and now is going towards the FDR. Looking at the future, there are also
Michele, can you
finished.
Can you end, please, very soon?
Sure, Ciska.
Yeah, so I would like to point out that we also have studentships and fellowships available. You can find out more about this at the ESO booth at this conference, the virtual booth. So I'm not going to go into detail in this slide. Next slide, please. And then in order to conclude, I would like to leave you with some positive messages that we are ready to resume observations as soon as the conditions will allow. We have been able to continue various kind of works during the pandemic, so that has been great. And we are at the beginning of making plans for the possibility of applying for time jointly on the ALMA and the VLT, so joint proposals. We didn't touch on this in the presentation, but this is an exciting opportunity that's coming up. And then finally, like I said, we continue to offer studentship and fellowships as usual. Thank you.
Thank you, Ciska. Thank you, Michele, for this exciting overview of highlights and exciting prospects. We're a bit over time, so I will just do the most popular question now, which is from Sandra Savaglio. And she's asking, why has the remote mode observations not been considered since we live in the digital robotic era?
For which telescope is this?
So this is with regards to the COVID situation. She doesn't say which telescopes.
Okay, so I can answer this for ALMA. What we have done is we have just recently taken the first steps of moving the control room from the OSF to Santiago. So there is now a fully equipped control room in Santiago. So you can actually run the observatory from there. So this is possible, but actually, unfortunately, people cannot even go into the office in Santiago. And so that is not a possibility right now.
And same for VLT, you need a lot of maintenance of the instrument itself. You cannot just leave them on the mountain in a non-safe state. So you need personnel to operate the instruments, and you need them to be up there, and it's not safe at the moment. So that's why it's gone. All the sites have been in safe state at the moment.
Okay, clear. Thank you. So I encourage everyone to continue the discussion and questions over Slack. Next, we move on to our next speaker, and that's Aline Vidotto from Trinity College at the University of Dublin. Aline obtained her PhD in 2009 from Sao Paulo in Brazil, where she worked on 3D magnetohydrodynamic simulations of magnetized winds of low mass stars. Then she went on to do a postdoc and a Royal Astronomical Society fellowship at the University of St. Andrews, and also a postdoctoral fellowship at the University of Geneva. And from 2016, she's been at Trinity College Dublin, where she's now an associate professor. In 2018, she was awarded an ERC Consolidator grant. And as I said, her interests are the theory and also observations of the interactions of exoplanets with their host stars' winds. And she's particularly an expert on 3D MHD simulations. And today she will talk to us about stellar winds and their effects on exoplanets. Aline.
Hello, everyone. Thank you all for watching from wherever in the planet you are. And in particular, this is such an honor for me to be giving this plenary talk. So I also want to thank the SOC for giving me this fantastic opportunity. Today, I want to bring you in a journey in the story between how a star and a planet interact with each other. So just to start, what I mean by star during this talk is low mass stars. So I'm thinking about stars that are either fully convective or they have a convective outer envelope. And convection here is key because it drives magnetism. Magnetism then drives the stellar winds, which then interact with your exoplanet. These stars are also the majority of known planet hosts we have at the moment. So stars in this talk means low mass stars. Right, there are several different interactions between a star and a planet. The obvious one is the gravitational force between these two bodies, but there are other different interactions that arise, and I have here listed 4 interactions in this diagram. And each one of these interactions, they can cause an observational signal either in the star or in the planet. Now, when you want to observe these interactions, you then go through a large range of wavelengths through the electromagnetic spectrum. It's super cool science, but this diagram involves a lot, and I'm not going to talk about the details of each of these interactions. Today, I'm going to focus on the last 2 of them. So I'll talk about how stellar winds and how radiation from the star can affect the atmosphere of exoplanets. So that's my storyline. I'll start this talk telling you the story from the exoplanet point of view, and then I'll move on and tell you the story from the stellar point of view. And at the end, I would like to merge these 2 different points of views. So starting from the planet, the first question you should be asking is, what is the relevance of studying atmospheres? Of what is the relevance of having an atmosphere for the planet? So one fundamental question regarding life is that we believe atmospheres could help develop or sustain life in a planet. I'm not going to talk about habitability today. The other point that I show here on the right side of my slide is on how atmospheric losses can sculpt a planet. So you have here a histogram of a planet, a number of planets as a function of the size, the radius of the planet. And you see that there is a depletion of small planets. And we believe that these planets, they evaporate, so they lose a lot of material. So they are born big, but then with time, they become smaller and they pile up on the left here. So atmospheric losses changes also the mass radius distribution in planet population. You can think of this as similar to a stellar wind that removes mass from a star, and as the star mass becomes lower, the evolution through the HR diagram changes. It's the same thing happening here with planets. Now, if you want to detect these atmospheres, there is, for example, this indirect method of the histogram I showed you. But there is also a less indirect method, which is looking at transmission spectroscopy or spectroscopic transits. So imagine you have here your star and the planet is transiting. Now you take the spectrum of the star when the planet is out of transit. You take another spectrum of the star when the planet is in transit, and you subtract the 2. Whatever remains is the atmosphere of the planet. So if I want to plot the light curve, looking now just at the broadband optical, so you're just looking at the geometric disk of the planet. When the planet passes in front of the star, you see this small dip in the light curve. Now imagine this planet is losing mass and its atmosphere is in this asymmetric shape. So when I observe this planet, suppose this is now a hydrogen-rich atmosphere. When I observe this planet, what I see is the Lyman alpha line that gets absorbed and transmitted through the atmosphere of the planet. Now, when I see this light curve, what I have is a very asymmetric and much deeper transit light curve. And this technique has been used now for a number of planets. The number is not really large, but there is one case that I would like to highlight because I think this is so fascinating. So this is a planet, a warm Neptune, that orbits an M-dwarf star, so a small star. If you have very good eyesight, you're going to see that this is a light curve in the optical. So this tiny little thing here is the transit depth when the planet transits in front of the star. Now, the huge transit that you see now in blue is actually observed in Lyman alpha lines with the Hubble telescope. You see that in hydrogen, this planet seems much bigger. The transit depth is 60%, so it's a lot larger than we had in optical. The interpretation is that this planet is losing a lot of atmosphere, so this is called through an evaporation process, and it forms this comet-like tail that transits behind the planet. The escape rates that have been estimated from this planet ranges to 10 to the 9, 10 to the 8, 10 to the 9 grams per second. So let me go a little bit more in detail of what is this so-called photoevaporation. Now you have your star and you have your planet here. Your star is emitting high energy photons. In particular, I'm interested in the UV and the X-rays. So these photons, they penetrate deep in the atmosphere of the planet. They deposit energy, they heat, and therefore the atmosphere expands a little bit. And therefore it more easily leaks, more easily evaporates. So this is called the photoevaporation process. You can imagine that if your planet has a lower gravity, it's going to be more difficult for this planet to hold on to its atmosphere. So evaporation rates are larger for low gravity planets. The same way, if your planet is receiving a lot of high irradiation from the star, either because the star is active or because the planet is very close in, you also see more evaporation. As a result, what we see are very dense outflows getting out of these planets, and we use in general hydrodynamic simulations, radiation hydrodynamic simulations to study atmospheric escape. I have here now an illustration of this effect, the effects of a gravity on the evaporation of a planet. So this is done in a 1D code. The planet is located at 0.045 AU. In this case, it's orbiting a sun-like star, so the same UV flux as the sun. What you have here are two planets, the low mass one and the higher mass one. And you see the differences in escape rates already. You see that the lower gravity ones has increased atmospheric escape. Now, the plots on the bottom here shows the velocity, the temperature, and the density of this atmospheric, this outflow, this escaping atmosphere, which we then use to create synthetic observations, to create synthetic transmission spectroscopy observations. I'll come back to this point in a couple of slides. But what is interesting is that the UV of the star is the same, and it affects differently these two planets. Now, what happens when the UV of the star is no longer the same? This is a super cool work that I suggest you read. It's showing, this plot on the left is showing an X-ray luminosity or the UV luminosity of the star as a function of age. And what you see is this decline of high energy irradiation from the star as the system ages. And this happens in low mass stars. So as the star becomes less active, there's less UV flux. And although the general trend is a decrease, you see also that there is quite a spread. And the spread here is because the star retains its initial condition. So if the star is born as a fast rotator, it is going to overall during its life have more EUV flux than if the star is born as a slow rotator. Now you can imagine that if your planet is orbiting a slow rotator or a fast rotator, the history of the evaporation of this planet is also going to change. And I show here on the right what would happen to this planet if it was orbiting stars that are fast, intermediate, or slow rotators. And evaporation rates here are very large at young ages, and it declines with age. What we can calculate as well is the amount, the integrated amount of mass that this planet loses during this evolution. And in this case here, it can lose up to 20% of its initial mass. Now, we then use these atmospheric profiles to calculate the spectroscopic transits. So these are predictions of observations in Lyman alpha and in H alpha. Model here only considers hydrogen. So the color is the following. This is the line profile. So the larger the delta F is, the larger the transit depth. And here's the velocity or wavelength of the line. So the color indicate blue for the very young system, getting to lighter colors for older systems. And you see that there's not much fun in the Lyman alpha line in a way, because it's all fully saturated. It's also broader at younger ages because the velocities of the outflows are larger. For H alpha, you see the transit depths, they can be 3 to 4% larger in excess of whatever you observe in the geometric transit. So it is possibly observable. The point here is that when the star is very young and it's very active, it's very difficult to disentangle the planet and the stellar signature. Right, one thing you see in my line profiles is that they are all symmetric. That's not really what observations show us. And the reason why they are symmetric is because I'm ignoring the stellar wind. So now I'm going to move on to tell you the stellar side of the story. And I start this with my plot indicating or sketching the differences between planets in the solar system and exoplanets. On the left, you have the sun and the earth at a distance of 1 AU, or in units that matters to me, this is 215 our sun. And here we have a typical hot Jupiter. So this is HD 189733. So this planet orbits at 0.05 AU, which is around 6 stellar radii. Now, if you think of the solar wind around the Earth and the stellar wind around this exoplanet, they have completely different characteristics. To begin with, around the Earth, we have a very low density wind. We have very low magnetic fields. But if you bring your planet very close to the star, now you have a denser environment and a higher magnetic field environment. So the velocities are perhaps comparable, because on the one hand, at the Earth, the solar wind has reached this asymptotic speed. Therefore, it's a high velocity wind, 400 kilometers per second. It could be larger depending on the magnetic cycle of the sun. And on the other hand, if the planet is too close to the star, the wind is still accelerating, so velocities might not be as large. The difference actually comes because the planet is also in a Keplerian motion. So if you assume circular orbit, velocity goes 1 over square root of the distance. Therefore, the closer you are, Keplerian velocities are larger. So the headwind, so if you are in the planet reference frame, what you feel is not just the wind of the star, but is also the motion that you have through the wind of the star. So putting all this together, we know that solar system planets, they feel a lot less interactions or less extreme environments as when you compare to exoplanets. Now, the interactions between a star and a closing planet, they can happen in a sub-Alfvénic regime or a super-Alfvénic regime. So imagine you have your star, now this is the stellar wind, and you have a point when the wind accelerates to above Alfvén velocities. So you create a sonic, an Alfvénic surface. Now, if your planet is beyond the Alfvén surface, no perturbation can go back to the star, so the star doesn't know much about the planet. So this is analogous to the sonic surface in hydrodynamics, and I'll come back to this in a minute. So you have a planet that is orbiting in a sub-Alfvénic regime. Now this planet can connect directly to the star. And what you see here is a case where you can transfer energy, you can transfer angular momentum from the planet to the star and back. This can also create hotspots in the star, because if you assume there is a flow, imagine you have a flow going towards the star. As the flow impacts the foot points on the stellar surface, you can then create a hotspot. So this is an interaction in the sub-Alfvénic regime. Let's look at an interaction in the super-Alfvénic regime. Now what you have here is a star and an evaporating planet. So this is further out from the Alfvén surface. And you see here on the left side, a formation of a bow shock. It's very tenuous, maybe not seen in this image, but if you download the paper, you'll see it. And you also see the comet-like tail that is formed. So this is the evaporating material that is left behind. Depending on the characteristics of your star, of your planet, of the stellar wind, this evaporating material, they can actually cause or create an inspiraling accretion stream that then travels towards the star. So the differences between left and right panel is essentially depending on the physical properties of the system. So now I told you about the effects of radiation in the evaporation of the planet. I now gave you a little bit of an introduction on stellar winds and how these winds could affect planets. Now I want to merge the 2 points together. So you have your EUV and X radiation affecting or creating photoevaporation in the planet, but now you have the stellar wind coming in and blowing part of this atmosphere out. How can stellar winds affect atmospheric scape? Maybe several ways. One possibility is that it can erode the atmosphere. So we believe this happens in the case of the young Mars, when the solar wind was much stronger, eroded atmosphere of Mars. Mars don't have a protective magnetic field similar to the Earth. It could also create atmosphere. I'm not going to discuss this today, but this is created through a sputtering process. It could do nothing. Hopefully that's not the case, or I don't have a job. But what I want to talk about in the next slides is the idea that I have put forward, that the stellar wind could actually prevent or reduce atmospheric escape in closing planets. And the idea is the following. Imagine, this is a sketch, you have a planet in the two panels. The planet is losing atmosphere, so the atmosphere evaporates, it goes from very low velocity to high velocity. And the difference between the left panel and the right panel is where the interaction takes place. In the left panel, the interaction takes place above the sonic point, so above the sonic surface of the planetary atmosphere. In this case, the stellar wind shapes the outflow of the planet, but the stellar wind doesn't affect the evaporation of the planet. It's like your stellar wind wants to talk to the planet, but the planet can't listen to what the stellar wind is saying. Now, on the right-hand side, what I have is the opposite. Your stellar wind is either stronger or the evaporation is weaker in such a way that the sonic radius is beyond what is the interaction, where the interaction is happening. Now, in this case, the stellar wind can talk to the planet and can say, can you please stop sending mass? Can you please stop evaporating? In this case, the planet can reduce its evaporation rate or even suppress it. We did a parametric study with a 1D model for evaporation. So this is the surface gravity of the planets that the parameters we used versus orbital distance, or for us to have a quick idea, UV flux is plotted on the top axis. The color shows evaporation rate. Now, I divide this diagram into two. The part where I say the planetary outflow is not confined, so the left panel I had in my previous slide, or the part here in this diagram where the planetary outflow is confined by the stellar wind. Now, the colors here indicate evaporation rate, but in reality, if you believe what I'm saying, these models, they are actually over-predicting escape rates of planets, because at the end of the day, the stellar wind is also going to affect the escape of these planets. And it's interesting, when we were writing this planet, there was the observation of Pyman C that became available. So this is a planet that was expected to show a lot of atmospheric escape, but none was seen in Lyman alpha. And I remember suggesting, well, this could be due to a confined wind. It's definitely a case that we could study further. Now, what I want to show in my final slide is on a very recent discovery. So the announcement came last week, about a week ago. So this is a unique B. So this is a Neptune-sized planet orbiting a very young star. So this star has only 22 million years old. And now we are in a bit of an impasse here. We have a star that is very young, so there is a lot of UV coming out from this star. This planet receives this UV and should be evaporating like crazy. But on the other hand, because the star is very young and is very active, it has a high magnetic field, it should also have a very strong wind. And in fact, theoretical estimates show that winds are between 10 to 1,000 times have higher mass loss rates than when we compare to the solar wind today. And now, if I say, if this star has a very strong wind, then maybe it will reduce, or maybe it will stop the evaporation of the planet. Well, to understand a little bit of this dichotomy, we did some 3D hydro simulations. So this is not magnetic hydrodynamic simulations. The lines you see here, they are streamlines of velocity. So the planet is on the center. The difference between the first and the second panel is that the stellar wind that is injected in the grid, in the simulation, is either 10 times the solar mass loss rate or has 1,000 times the solar mass loss rate. And you see a lot of difference between these two scenarios. In one case, the atmosphere expands more. And of course, in the other case, because of the larger run pressure of the stellar wind, the atmosphere is confined to a smaller volume. The escape rates here is not actually that much affected. It's a reduction of 50%. But now if I look at the Lyman alpha absorption, and now I divide it here, it's in blue and red. And when I say I should apologize. This is done by my PhD student. And what Stephen Carolan did here, he divided the lines into blue and red wings. And what you see here is a variation of this absorption as a function of the stellar wind mass loss rate. And you see that, first of all, the stellar wind makes the line profiles very asymmetric, more absorption in red than in blue than in red. But secondly, it also reduces a lot the signature you would want to detect when you observe this planet. So transit signatures are erased by stellar winds. So this is a kind of a sad situation, but on the other hand, if you were to observe some transits of some signature, you could also tell something about the stellar wind itself. And I'm all in favor about using planets to tell more about what the stars, about the characteristics of the stars. So just to conclude, closing gas giants, they lose substantial amounts of atmosphere through a photoevaporation process. Atmospheric loss is enhanced if your planet has a lower gravity or if it receives a lot of energy from the star, either because it's orbiting close to the star or because the star is very active or very young. But stellar wind can reduce atmospheric escape and could erase these signatures, especially in young systems. Thank you very much.
Thank you, Aline, for a beautiful and clear talk. So we already have one question from Andrea Negri. Nice and very informative talk. Are there observations of exoplanet gas escaping of elements other than hydrogen?
Yes, there are. Oh, this is super cool. So there are, of course, you're still using Hubble in the UV. You have been detected carbon and oxygen escaping planets. But I didn't have a chance to talk about this today. But from the ground, there has been more and more observations now that are reporting helium. So you can look in the infrared, in the helium triplet, in the infrared, and you can also you're now, due to spectrographs that have very high resolution, you can now start seeing helium also escaping the atmospheres of these planets. So there are metals that are observed with Hubble, and also now helium from the ground.
Thank you. While people are thinking, let me ask a question. So you mentioned that winds can also create stellar atmospheres. Can you explain how that works?
Mm-hmm. So the idea is that if you have a terrestrial planet, it's very similar. In this model, we use an inspirational model from Mercury. So imagine you have a rock, a bare surface. If the stellar wind comes in, there is a certain kinetic energy that when you interact with the surface of this planet, you can actually sputter some particles. And these particles, they end up around the planet and they form this very tenuous exosphere. So that's we did this work in 2 transiting terrestrial planets, HD 219134, P and C. And we show that there is formation of volatile, refractory, an atmosphere of refractory elements, but they are very tenuous. So I don't think we have capacity to observe them, unfortunately.
We have a question from Tobias Boychert. Great talk. I was wondering if mass loss via evaporation can't take place towards the far side of the stellar wind in the cases when you expect a quenching of evaporation.
In the far side. So the stellar wind, we assume, is coming through all the surface of the star, right? So you have magnetic fields that could confine, that could prevent or create dead zones, but the stellar wind permeates the whole volume. Now, if you're thinking about the planetary evaporation, then it is true that if you're in the day side, you receive energy from the star, so you evaporate more on the day side. While in the night side, you don't have the same amount of energy input that you see in the day side. So you might have less evaporation in the night side. So our models at the moment, they are not very sophisticated, that we are not treating the night side, but there's a number of groups in the world that are simulating winds in a slightly planetary outflows in a slightly different ways that we are doing, where they also take into account the shadow of the planet. So yes, you can suppress some of the escape in the night side.
Thank you. So I'm afraid the other questions will have to be moved to Slack. Thanks again, Aline. Our next invited speaker is Volker Springel from the Max Planck Institute for Astrophysics. Volker obtained his PhD at the MPA actually in 2000. Then he did a postdoc at Harvard and then returned into the MPA as a group leader in 2005. In 2010, he became a professor and group leader at HITS in Heidelberg. And in 2018, he returned to the MPA as the director. Volker is well known in the field of galaxy formation simulations and cosmological simulations. He was the driving force behind many of the simulation projects from the Virgo Consortium and also with American collaborators, including the Millennium simulations, Illustris, and the TNG simulations. He wrote the Gadget and Arapaho codes, which are both widely used. And very recently, he was the recipient, together with Lars Hörnquist, of the Gruber Prize in Cosmology. So I'm excited to hear what he's going to tell us today about hydrodynamical simulations of galaxy formation. Volker.
Thanks a lot, Joop. I hope you can hear me all, and thanks for having me, and welcome to everyone. And I hope you're doing fine in these difficult times. I would like to give you a brief overview of this field of hydrodynamical simulations of galaxy formation. It's a wide field, and there are many things that are interesting, and I'll try to focus mostly on the methodology and some of the recent successes and try to highlight some of the challenges in this short half hour or so. In cosmology, as you know, we have a standard cosmological paradigm in which we know all the 6 parameters that determine it to exquisite precision. So that model is called lambda CDM, and it tells us the state of the universe as it was shortly after the hot Big Bang. The idea of cosmological structure formation on the computer is to take these initial conditions and evolve them forward in time. In principle, if it was possible to simulate all the physics, this would give you an ab initio way to predict how the universe evolves. Of course, we cannot solve the universe with all the details, so we have to make lots of approximations. And if we make them, we can still get an approximate model for how the universe evolves and predict things like the shape of galaxies today in a highly nonlinear evolved universe that looks very, very different from the initial state 13.5 billion years ago. And that's really the program of cosmological simulations, trying to make this bridge from the early simple state of the universe to the very complex state today. If this is possible, you can, of course, learn a lot about the dynamics that shapes cosmic objects. Now, if the dark matter is only simulated, then in the field we have made a lot of progress, I would argue, that because so-called cold dark matter simulations that simplify the problem by leaving out the baryons and just pretending they're also dark matter, these allow to make predictions for the dark matter backbone of cosmic structure, as you see here in this old image from the Millennium simulation. And it gave us the notion of a cosmic web at which, at the intersections of these filaments, large structures form, for example, a galaxy cluster at the very center of this image. These cold dark matter calculations of lambda CDM, they have also been very successful in explaining cosmic large-scale structure. This is shown here in this example, comparing large galaxy redshift surveys in blue to simulated galaxy patterns that you get out of some of these cool dark matter simulations. And on large scales, the galaxy clustering signal, by and large, is consistent with what's observed. And that has been an important validation of whether lambda CDM is viable at all. We can nowadays simulate the dark matter component of the universe across the whole range of scales where you expect structures. Recently, it has been possible to simulate the smallest dark matter structures that are expected, which are of Earth mass in the standard, WIMP-based scenario for what the particle mass is of a cold dark matter scenario. And here you have weakly interactive massive particles, say of 100 GeV or so. And then you have a thermal cutoff scale that says that the dark matter is ultimately not perfectly cold, but there's this finite, very small residual random motion left that restricts the sizes of the small structures you have. And they would be roughly actually of Earth mass. And those can be simulated, embedded in very large cosmological volumes, basically saying that we really can predict the structure over the full range of scales that is expected. And so as far as the dark matter is concerned, I would basically argue that the structure formation paradigm is fairly well understood. We can predict the dark matter halo abundance as a function of mass and time, as a function of, and we can predict also the clustering of these things and these objects, and that is instrumental to, for example, make accurate predictions for gravitational lensing, both with respect to weak and strong lensing. So that part of the story is relatively well computable these days, and all the different codes agree on that. But it's very different if you also include the dark matter. If you also include, excuse me, the baryons explicitly and not pretend it's also behaving as dark matter. So hydrodynamical cosmological simulations, they really aim to address the full problem of structure formation. And in the ordinary baryonic sector, about 5% of the cosmic energy density today, you of course have the stars that make up the luminous parts of galaxies. You also have supermassive black holes playing an important role. And already from these two components, it is very clear that if you try to simulate baryons explicitly, you have to address the formation of stars, which is in its own right an extremely complicated astrophysical problem. You have to deal with the growth of supermassive black holes because they affect galaxy formation in decisive ways. That makes that type of problem really a coupled multi-scale, multi-physics problem that could hardly be much more difficult. And one of the main difficulties lies, in fact, in the physics of the regulation of star formation in galaxies, because here you not only have to consider the radiative cooling of diffuse gas that leads eventually to gravitational collapse and then to star formation. You especially also have to simulate how the stars evolve and how they return back energy into the surrounding gas, for example, through supernova explosions, but maybe also through galactic winds, and of course through their radiative output. And the radiation fields of the young stars might influence surrounding star formation in important ways. The radiation field will lead to cosmic ionization, potentially affecting small galaxies in particular at high redshift and their star formation rate. And that's not all. The supermassive black holes in galaxies, we think, play an important role in eventually affecting star formation, especially in large galaxies. In addition, there are more exotic components like magnetic fields or non-thermal particle components like cosmic rays that provide additional pressure. And they also have been speculated to play an important role in galaxy formation. So this shopping list of physics here essentially must scare you if you try to make a computation accurately that simulates all of these processes right out of the initial conditions left behind by the Big Bang. But ultimately, that's what cosmological simulations of galaxy formation try to do in a highly schematic way, admittedly. But I will show you that many of them are nowadays fairly successful and make very interesting predictions. On top of these physics problems, You also have very severe numerical challenges. These are mostly at the technical level, but here you can discretize, for example, the hydrodynamical flows, which are complicated. They are highly supersonic. They exhibit a lot of turbulence. And again, because of the large dynamic range that you have to bridge, you need to devise highly adaptive techniques. And they are not always giving the same answer, even if they are applied to the same initial conditions with the same physics modeling. This shows an old example from our own work where we tried to simulate in a cosmological volume galaxy formation. And these images here, they compare the outcome here of the gas distribution in a disk galaxy that has formed here. And it was simulated with two different codes, a moving mesh code, a repo, and here an older particle-based code gadget with an older formulation of smooth particle dynamics. You see that the disks don't look the same. It's good that there are disks in both cases, but they're not of the same size. They're not exactly of the same mass. And also the so-called circumgalactic medium that you see around these disks is actually not the same. It's smoother in the mesh-based calculation and more lumpy and clumpy in this particle-based thing. So, you know, the code differences also matter, but the physics list that I described very briefly earlier is more important, as we'll see. The modeling of these so-called feedback processes in the baryonic sector, that's where the main uncertainty also lies in today's calculations, because these processes really determine the properties of galaxies, because they regulate, in particular, the amount of stars they form. Here, just to very briefly illustrate this, this is showing a short movie of the moving mesh technique that we developed, especially to simulate the galaxy formation process more accurately. Here, the gases are discretized on this tessellation that's created by a set of mesh-generating points. And these points move along with the flow and so let the mesh collapse, for example, into the center of a galaxy so that the tiles, which are here, or noise cells around these points, automatically get smaller. And because the discretized mesh is moving along with the flow, this method is particularly good to treat problems where you have highly supersonic flows, because the so-called advection errors can be largely eliminated in this technique. So we're fairly proud on this, but you know, as I said earlier, this sophisticated technique might not be ultimately critical to get successful galaxies. The modeling of the feedback physics is really the crucial part, even though I do think that it helps, of course, if you have an as good method as possible. Now, in this field, I would say that over the last 5-6 years, really transformative progress has been achieved. Several groups around the world have succeeded in creating large volume simulations, hydrodynamical simulations of pieces of the universe, and successfully predicting the whole galaxy population forming in these models of the universe. Here's, for example, the illustrious simulation, the Eagle simulation led by Joop, our chair, extremely successful. We have Horizon AGM, Magneticum, Massive Black 2, and also our next generation attempt, an improved version of the illustrious simulations I'll talk about more later on. These are examples. There are a few more, and I think it's really amazing how much progress has been achieved in this field over just a course of a couple of years. Here, to illustrate that from about 5-6 years ago in illustrious, maybe the most important result from this simulation was that it succeeded in predicting successfully the morphological mix of galaxies. This is illustrated by showing the stellar distribution in some of the dark matter halos that have formed in the simulation. And these visual stems, they give you an idea about the different galaxy morphologies that are found in these hydrodynamical simulations, including elliptical galaxies, and then also disk galaxies, some with bars, some without. And importantly, this morphological mix changes systematically with stellar mass. Towards more massive systems, you become more dominated by spheroidal systems, and vice versa. And this follows, of course, observational trends. And since this is not something that is pre-imposed in any way in the model, in tuning of the model, this is also, again, an important validation that the lambda CDM scenario, in principle, gives rise to a fairly successful description of the formation of the full galaxy population. What physics is required for this? Mostly it is basically these three blocks here. You have to include treatments in the diffuse gas of radiative cooling. This is the part that is perhaps least uncertain. We can fairly accurately compute the cooling rates, of course, to different degrees of sophistication, if there's additional radiation around and if you have metals. But I would say by and large, this can be computed fairly accurately. Then the gases collapse under the pull of gravity in the centers of dark matter halos, go into rotational support, and in the disks that form, you then have local gravitational instability leading to star formation. The real problems start in the second block when the stars then are forming. This you have to model with to different, in a very approximate way, because you obviously cannot follow the collapse of the gas all the way down to the ignition of nuclear fusion. At some point you have to decide now a star is going to form, and you base that either on heuristic descriptions coming from observations, or you piggyback on from more detailed smaller scale calculations. Then you have to account for the feedback of the stars that I mentioned earlier, account for the metals returned, and also for the finite lifetime. Eventually the stars explode and return energy to the star forming phase. The third block is also fairly difficult to treat, because at the centers of halos you have supermassive black holes. They grow through gas secretion, occasionally also through mergers with other black holes. And associated with the gas secretion, they liberate a lot of energy. At high redshift, they will shine as quasars, where they're extremely luminous. And over the course of the history of the universe, about as much energy is liberated from all the black holes combined as you have from all the supernova explosions combined. So you see from this argument that the energetics suggest that black holes can influence perhaps galaxy growth. And that's actually one of the prime hypotheses, and that's made in the field, and which we try to demonstrate through comparisons of the outcome of our simulations with observations, that this is actually correct, this hypothesis. Now recently in TNG we also added other things like magnetic fields. We made improvements to, in particular, the black hole treatment, and I'll get to this shortly. Let me then describe a bit these most recent project we have done in this area, namely the next generation luster simulation. This is the team that has worked for a number of years on these calculations. It was a joint work between Heidelberg Garching and Harvard and the MIT. And I think it was really a very fun project. And we produced essentially these three models, TNG50, TNG100, and TNG300. These are fully hydrodynamical simulations of cosmic structure formation embedded in boxes, periodic boxes of 50 megaparsec, 100 megaparsec, and 300 megaparsecs on a side. There are also accompanying dark matter only models so that you can, for example, investigate the impact that baryonic physics has on structural growth. We made the data of the simulations publicly available, and this has led to a very pleasing uptake of these models also in the field. Many people come up with their own analysis ideas, and it's really very nice to see that these type of calculations are very useful for studying many different scientific questions. And that's also very good because they are not exactly easy to do. You need a very large supercomputer to carry them out. TNG50, which is our highest resolution simulation, has consumed more than 100 million CPU hours on this large machine here, the High Performance Computing Center in Stuttgart. It's already dismantled, unfortunately. It's now replaced by an even more powerful supercomputer. And in this field, of course, one really benefits from the steady progress of computational capabilities. Of course, it's still very hard to design codes that exploit the concurrency that's needed to, for example, use tens of thousands of cores to then compute on a tightly coupled problem like galaxy formation is one, where different pieces are always communicating through gravity, and not only that, but also through radiation and also hydrodynamical forces, of course. Here's a short movie of formation of a disk galaxy. I hope you can see this, and it's not too jaggy via Zoom, but I encourage you to visit the TNG website, where there are many nice visualizations of the simulations that give, I think, are very helpful to develop also intuition about how cosmic structures grow, and how, for example, the gas flows into galaxies, as you see here at high redshift. This is a proto-galaxy coming together, still at redshift 2.3. And then the heyday of disk formation starts at about a redshift of 2, which is roughly reached now. You see that in the gas that's seen here in the big panel, you develop a rotation-supported gas disk. The stars are shown here in one of the insets down there. And you see that already by this time of redshift 1.5, a large disk galaxy has formed. On the left, you see in green the metals that have been expelled by galactic winds, and also the AGN feedback at the center. And you saw essentially that much of the halo is actually enriched. So the processes that mix heavy elements in the halo are very important and are predicted by these hydrodynamical simulations. So you can then use them to, for example, compare to observations where in the diffuse gas the metals are expected, and that will inform also about the efficiency of these galactic winds that you have seen in this movie.
5 minutes.
Yeah, so black holes are extremely important. As I showed earlier, we have revised our model of that in TNG and proved we've done this because we needed the quenching of galaxies in the red system. In red, large galaxies is basically blamed on AGN in the simulations that we are doing. And in TNG, we now obtain for the first time a very nice color bimodality that matches results and data from the Sloan Sky survey. And at the same time, these galaxies cluster in the right way, so they are quite consistent with the extremely accurate clustering data that you have in the local universe, from, for example, from the SDSS survey. And this agreement is then also quite true if you split up red and blue galaxies. The galaxies, they also come out, interestingly, with roughly the right sizes, both for late and early type galaxies, which is also a nice success. And if you look at more detailed distributions of morphology, here's a nice paper done by Vicente Rodriguez Gomez, where he looked at pan-stars images and processed images of galaxies from the illustrious TNG simulation in the very same way, and looked at this here in this multi-dimensional plane of Gini coefficient M20 in concentration. You see that the morphology of the simulated galaxies really matches fairly well what's observed to a degree I actually find surprising. This is also quantitatively pretty much the case. Here you see a trend of, for example, the bulge strength as a function of stellar mass. So these galaxies have roughly the right bulge sizes. This wasn't true, for example, for our earlier simulation illustrious that was way off from the data. But not all is good if there are tensions in a lot of details. Here, for example, is again the bulge statistics as a function of stellar mass. And you basically, if you look at this, you see that there is no good correlation between morphology and galaxy color. That's too weakly expressed in the illustrious TNG simulation. And this probably points to deficiencies in the way the black holes are modeled. What's also new in our simulation is that we can predict magnetic fields, and the magnetic field strength profiles that are arising from the amplification of the magnetic fields are in good agreement with observations. This is because the small scale dynamo that drives the amplification of the magnetic fields is basically saturated once the magnetic forces become comparable to the thermal pressure forces. And that's something that's also observed in our own galaxy, where you have equipartition between the thermal pressure and the magnetic field pressure. So the simulated galaxies, they reproduce this, and they produce also Faraday rotation measure maps that are in good agreement with the data that we have on the magnetic field strengths in external galaxies. And talking about magnetic fields, in the last 2 or 3 minutes, let me mention that in current work, lots of groups study maybe another missing ingredient in the current generation of cosmological simulations. These are namely cosmic rays. And in isolated simulations, it has been shown by multiple groups that if you include cosmic rays created in supernova remnants, mostly by diffusive shock acceleration, then you have a two-fluid system in the simplest treatment composed of thermal pressure and cosmic ray pressure. The cosmic rays, they can be transported relative to the thermal pressure, and then you get something what's called a cosmic ray-driven wind and outflow. And that's of course important if the galaxies lose baryons through such a wind. That's going to affect the stellar mass. And the regulation of star formation is the main challenge in these simulations. And in our own work, we have done for a number of years initial work also on isolated toy simulations. They have shown that the cosmic ray winds, they have a mass loading dependence with stellar mass that's very interesting. The mass loading goes strongly up towards the dwarf galaxy scale, suggesting that they would be important, especially for small galaxies, while the energy loading in these winds is constant. And both of these 10 dependencies are essentially what we assume in our Elastos TNG simulation models for the winds that are put in by hand there. So cosmic rays are potentially a missing ingredient. And I just want to mention this essentially, this fact, and say that at the moment, the field sees a flurry of activity in that. We have also tried to apply cosmic ray physics for the first time in cosmological simulations of Milky Way-sized galaxies as part of the Auriga project and extensions thereof. Here we see a Milky Way-sized galaxy forming at high resolution without cosmic rays. These models look fairly realistic overall and are very interesting in their own right to study the fate of formation of the Milky Way. While if you include cosmic rays, the morphology changes a lot, depending on what assumptions you make for the plasma physics of cosmic ray propagation. In the most realistic scenario we have, there is still a fairly large disk, but even then it is modified. The reason for that is that the circumgalactic medium is affected by the cosmic ray pressure, as you see here in the gas flows of these models. And depending on what physics assumptions one makes for the diffusive transport of cosmic rays, you obtain different results for the forming galaxy. So it will be very interesting, I think, in the next years to understand really what is the interplay between other feedback processes and cosmic rays. And I think we'll see a lot of exciting work there in the next years. So I'm at the end of this talk. I try to give you a brief overview of recent hydrodynamical simulations progress on successfully forming galaxies in lambda CDM. Many groups have made great strides on that in the past years. I think they all agree that at the moment that for very massive galaxies, we rely on AGN to quench star formation there. And what some simulations can also do nowadays is to include magnetic fields and then kind of self-consistently predict via dynamos the appearance of galactic magnetic fields. And here, this seems to be almost effortless that they come out about right. Of course, we'll have to cross-check these results further with different groups and different codes and different modeling assumptions. And at the end, I gave you a glimpse of cosmic ray physics, and that might change the whole story yet again. Thanks a lot.
Thank you, Volker, for an impressive and inspiring presentation. So we have a number of questions. Yves Revaz is asking, how can we persuade ourselves that the successful reproduction of galaxies is not biased by choices of the many poorly constrained parameters of subgrid models?
Oh, I think that's a question that comes often up. First of all, I mean, there are not that many free parameters that, as some people imagine. We of course fit certain observations at low redshift. For example, the stellar mass halo mass relationship that expected. So the strength of the feedback is basically dialed up to yield a correct result there. And then you have to, I think, check for consistency what other predictions you make. And these type of calculations are incredibly rich in the variety of things they predict. So I think it is not reasonable to assume that all of these successful predictions can be tuned by these parameter choices. In fact, they can't. But ultimately, we do learn from discrepancies. So I don't want to overstate the successes of these models, even though I think they are fairly successful. But what they really are most suitable for are to look at discrepancies, and then you can often find out that no matter how much you change your parameters, there's no way that you can resolve the discrepancy. And at that moment, strictly speaking, your theory is invalidated, and it tells you that something is incorrect, either in the cosmological assumptions or in the physics assumptions or in the numerical treatment. Of course, there are many possibilities, but I think the overall success of the simulations describing in a huge variety of different things correctly is, in my opinion, a very compelling validation that the lambda CDM paradigm is plausible. And you see this especially if you drop certain things. For example, leave out the dark matter or so. I challenge anyone to come up with anything that even looks remotely as successful as the simulations I discussed.
Okay, one more question, if you can keep the answer brief, please. Leo Burcher is asking, well, he's saying, you said there are still deficiencies in the way black hole feedback is modeled. Can you say what kind of observations you would need to improve your feedback recipes?
So from the theoretical point, the problem is the dynamic range. So we have to make fairly simplifying assumptions. So I think we need additional, constraints. For example, that test predictions we make. For example, we predict a correlation between the disk sizes and the recent mass growth of black holes. So this is something that, to my knowledge, no observational paper has yet highlighted. So I think we should ideally test our models by looking for such things. Certain correlations that the simulations show, and then go directly into the observations and see whether that's confirmed. Maybe it's already enough to use archival data in some cases to look for it. And sometimes you maybe have to devise a dedicated observational program to check these predictions.
Thank you very much. There's a lot of other questions that people want answers because there are a lot of votes received, but we'll transfer those to Slack, and you can also ask additional questions on Slack. Thank you, Volker, and thank you also the other invited speakers. Next on the program is the closing ceremony, even though the conference will go on for another half day. And the closing ceremony will be led by Roger Davies, who is the president of the European Astronomical Society. Roger.
Hello, can you see me and hear me?
Yes.
Good, thank you very much. Well, an enormous amount has happened this week, and it seems a very long time since I spoke to you at the opening ceremony. But I want to cast your mind back further than that to March, when we decided to hold this meeting online. It was incredibly difficult to imagine an event of this scale and breadth being a success then. To be honest, we had in mind a rather smaller event. And so my first remark is to thank everybody for attending and making this event the stimulating and exciting week that it's been. And what a huge amount of activity there's been. 1,777 participants from 58 countries, 986 talks, 524 e-posters, 16 symposia, 21 special sessions, and a further 14 from the Royal Netherlands Astronomy Club, 11 lunches, 18 plenaries and related things, and the whole lot carried out on 11 parallel sessions. There's also been actually a huge amount of interaction, more than we could have ever imagined. 1,487 people signed up on the Slack channel. There were 7,000 messages every day. The scientific sessions have been absolutely outstanding. We've been spoiled for choice and blown away by the quality and the innovation of the presentations that have been given this week. So, although, of course, we were forced to do this because we couldn't have a face-to-face meeting, there are many advantages, it's turned out, to doing a virtual meeting. And one, of course, is that you can see the presentations that you would have liked to have seen but missed for up to a month after this meeting. Another advantage is that we're able to enjoy contributions from colleagues around the world. In the mornings, we were able to catch up with presentations from Asia and Australia, and later in the day from our friends in the Americas. Look out this afternoon for the session on the impact of satellite constellations on astronomy. This is a truly global issue which we'll need to tackle with the EAS, the IAU as well. It's been an enormous event, and there are many people that I want to thank in this closing session. And at this point, I need to share my screen. So if I do that, does that work? Let's do that. Yes, here we go. So this is a slide that shows the Cooni team who supported us. Now we've had a partnership with the Cooni Congress for a number of years now. And so a few people on the screen, Frank Grosset, Laurie Bosson, and Audrey Rocher, I know myself, and we've worked with them for a few years. But for this activity, they've had a team of 25 people supporting us, who worked very hard for a couple of months, essentially, often round the clock, for many weeks, and particularly this week, to support our activity and make this Congress a success. They, in turn, were supported by the staff from Centium, who developed the on-air platform. What has been achieved could not have been achieved without their enormous commitment. So I'd like to thank them very much for all the work they have done for us, and I look forward to working with them again in the future. So now I should probably unshare my screen. How do I do that? How do I unshare my screen?
On the top side of your screen, you will see a stop share in red. If you click that, then you're gonna stop sharing the screen.
I only have the little, there we go. Somebody did that for me, thank you. Thank you very much. There's another example. Okay, so the Cooni team has been absolutely crucial to being able to pull this off. And we're all very, very grateful to them. The other huge team that's put in a huge amount of effort is, of course, the home team in Leiden. And I want to pick out a few people for a special thank you, but I know there's a big team behind them. So Alexander Schouten, Leo Bircher, Huub Röttgering, Joop Schaye, and Marika Bahn, as well as Simon Pottiges-Zwart and other NAC organizers. They've put in a huge effort, and we rely, as the EAS, we're a very small organization, we rely on the local hosts to take the burden of making the local arrangements and shaping the scientific program. You all deserve great credit for what's been achieved at this meeting, and of course, extra plaudits for your willingness to host again next year. Thank you very much indeed, and I look forward to thanking you personally in 12 months' time. It's my pleasure to also thank the council members of the European Astronomical Society, and both past and present, for their service on the annual meeting board. That's chaired by Lex Kappa. The other people involved are Sarah Lucatelli, Johan Knappen, who was the treasurer, Nick Kilafis, who is the treasurer now, and Mark O'Dar, our executive officer. The board works tirelessly to bring this meeting to you, and it's a great pleasure to thank them for their efforts. The other people to thank are the sponsors and exhibitors and our organizational members. We always get a great deal of support from them. I hope you've enjoyed interacting with them through the online channels. I'd particularly like to call out the Merak Foundation, Their prizes are very important to us, but particularly for the opportunities they provide the young prize winners to build their careers. So now to the heart of the meeting, the symposium organisers and special session organisers. In many ways, you are the absolute centre of our activities during the annual meeting. It provides anybody who wants to propose with the opportunity to propose a session on your favourite topic of the moment, and if you're selected, you can concentrate on the scientific programme and delivering it absolutely to its best, and more or less allow the organisation to be taken care of for you. The opportunity to propose for the Leiden 2021 meeting will open later in the summer, and I encourage all of you to think about what you'd like to see in the symposium next year. So, Kuoni team, Leiden team, board members, session chairs, you can be truly proud of what's been achieved at this unique week. Thank you very much indeed. So I want to congratulate the plenary lecturers and prize winners. They've treated us to some thrilling results and spectacular presentations. We're looking forward next year to the inaugural Zwicky lecture by Martin Rees and the first award of our new Inspiration Prize. What really impresses me about the programme for this week is its enormous breadth. You all have your personal highlights, but what struck me was the great range of topics that was covered. One day I was learning about a project based at the IAC in the Canary Islands to assist refugees from the Western Sahara. And the next day, I was listening to the exciting results from the new X-ray satellite eRosita. There are so many jewels for you to watch later, and now that we have the opportunity to do so. Today is Inclusion Day, where we showcase the efforts to make our subject accessible to people from all backgrounds. As part of that effort, the Society has adopted a new statement on equality and racism, which is on our website. We've also decided to award a new prize, the Inspiration Prize. The criteria for awarding this prize are on the Society's website, and I invite EAS members to suggest names of astronomers, living or dead, that best fit the spirit of this new prize. Together with a short case, you could email your nomination to the EAS office, please no later than 2 weeks from today, July the 17th. So before inviting Professor Huub Röttgering to tell us about plans for EAS 2021, let me remind you to nominate candidates for our prizes, the MERAC prizes in observational astrophysics, theoretical astrophysics, and for advances in instrumentation and simulations. In this cycle, it's for the early career researchers, the Tycho Brahe Medal, and the new Inspiration Prize by the deadline of the 31st of October. Okay, so it's now my pleasure to hand over to Huub to advertise Leiden 2021.
Let me share my screen. Yes. Can you hear me and see me? Joop?
Yes,
Yeah.
we can hear and see you.
Good. This was fascinating, exciting. I really enjoyed this, and behind the scene, of course, it was kind of like thrilling to really see whether this would all work, and the answer is absolutely yes. I mean, it basically was flawless, which was great. And I really would like to echo Roger in thanking Kuoni, EAS board, the local people, and especially the postdocs, PhD and master students that helped. And I won't go through the long list, but thanks a lot. Without all your help, this was not possible. And let me also thank Roger Davies, because he couldn't thank himself, but he is a real positive force behind the scenes and now on the screen. So thanks, Roger. Thanks for all what you've done. Okay, so next year there will be the next EAS. You see here the dates, end of June, beginning of July. And we hope to basically host it here and that people can really come. Because I fully appreciate that remote meetings are effective and good, at the moment necessary, but I also really miss seeing all of you. I miss the coffee breaks, the lunches, the dinners, etc. And so please be very welcome. We booked a fairly large place to where we can hold those conferences. It's really close to the observatory. It's a 10-minute walk from here and maybe a 20-minute walk from the center of Leiden. So it's ideal. It's also not overly expensive, so we're very happy that we can go there. And we really need to discuss with all of you the format. I mean, should we do something mixed, remote, normal? So that what I've heard is that we can have speakers from the States that can basically give the presentation remote, and within Europe you can basically can all come here then maybe by train. There was also some discussion also among members from the EAS board whether we should minimize travel by maybe have other meetings in the neighborhood. The neighborhood might be Belgium or Germany or London. And so that basically people have maybe one big trip for 1 or 2 weeks where they basically do a lot of their social networking. And we need to think about how to do that, but let us know. And as Roger just said, please start thinking about sessions. Okay, we'll do it in Leiden, but Leiden is part of the province Zuid-Holland. And there's lots of industry here, lots of research, education, technology, all centered around space research. Of course, there's ESA and other companies. There's our Leiden University, but there's also Delft University, and there's a whole host of other companies. What's interesting is that Esron is moving the Utrecht building to our premises, and they hope to be completely working in their new building in the summer 2021. And if you look then the whole landscape in Holland, this is basically it. And I use this interesting map because you can see it in color. Green is safe, and the blue bits are basically under sea level. So we would really like to welcome you in Leiden, Zuid-Holland, and it's not all under sea level, but you see where it is. And to sketch the landscape, I mean, in Leiden there's a university, there will be the big building of Esron, and then at half an hour biking distance there's the ESTEC, where there are well over 3,000 people working to basically help building satellites and help launching them. So we'll certainly team up with them. If you then go to Schiphol, then you can either in 20 minutes you're in Leiden, or in another 20-25 minutes you're in Amsterdam, where there's another very important astronomy group hosted by the University of Amsterdam. Nijmegen, they're fairly young, but very active and vibrant. For example, Heine Valker is there, who has leading part of the European team on the black hole cam and the beautiful images of the black hole. If you go to another part, there is Groningen University. There's also a department of Esron there, and there's Astron. Astron basically runs our radio telescopes, Westerbork, LOFAR, and they also have a big stake in Schaye in terms of building equipment and also building software. A central role within Holland is played by NOVA, and NOVA coordinates basic research done at the 4 universities, and they also have a big stake in optical instrumentation, where the link to ESO is crucially important. Yeah? So if you want to come, yes, you can go to Schiphol, but you can also take the train. And there's a very nice interactive map built by Knut Janke, and there's a link there, and maybe someone can post it on Slack. And there you can see basically all of Europe. I mean, you can basically come here by train. And so look at that and consider that. Zoom in, and if you go to the page, you can zoom on the line, you see how long it takes, etc. So I think this is part of the future. Thanks, Knut, for basically building this. And then I can tell you about Leiden, about the restaurants, museums, shops, etc. But there is a rather smooth a few-minute movie about it, which is probably much nicer to see. It's a bit too flashy maybe for scientists, but on the other hand, let's enjoy it. So can I ask someone of the Coroni staff to start it? And then I stop sharing my screen. Sure. And it takes a few minutes, and if you leave because you think it's too commercial, that's fine, but it's nice. And hope to see all of you next year, and either in person, and if there's no other options, remotely. So thanks all of you for attending. Thanks Coroni, EAS board, all the people that helped. It was great. I really enjoyed it. And don't forget, we are not stopping yet because there are great sessions this afternoon. Thanks again.
Okay, thank you.
Thank you very much,